This video is for Math 155, Calculus class, and it is Chapter 25.6, Simpsons Rule. Okay, we've talked a little bit in the past about, the last few classes, about finding the area under a curve to approximate the definite integral. Remember, definite integral is between two given points. We used in a long time ago when we started integration, we talked about limits, and we looked at rectangles under a curve, and we had noted that the smaller the intervals got, the better our approximation was for an area from, say, 0 to 1. And then with the trapezoidal rule, we did the same thing, actually, except we used trapezoids. So we evaluated between two endpoints, 0 and 1, in that interval, and then we actually looked at the trapezoids. And it's the same kind of thing, except we use the trapezoid formula to approximate it even better. Well, the third way to approximate it is using Simpsons rule. And Simpsons rule actually uses parabolas. And we don't get into how that happens or why that works. Pretty much our book focuses on, here's the formula and let's just learn that. Again, this is technical calc, so you learn how to use the math instead of the theory behind the math. So I'm going to go ahead and get started and show you an example of a problem. This is on page 764 in your texts, and it is problem number 3. And we have an interval from 0 to 2 of 1, here's the function, 1 plus x to the third dx, and you're given that n equals 2. Now, there's a lot of similarities between, let me write that better, that doesn't look very nice. There's a lot of similarities between the trapezoidal rule and Simpson's rule. And one is that we continue to find h the same way, and h is equal to b minus a over n. Remember, here is your a, here is your b, okay, and our n is 2. So we would have 2 minus 0 over 2, which is 1. H equals 1. That means our increments will be in a value of 1. So we start at 0 to evaluate this definite integral, and then we'll go into another increment of 1, and then we'll keep adding increments of 1 until we get to 2. Now in this case, that's only going to give us 3 points. But just to help you understand what the book does, it says x sub 0. X sub 0 is going to be your a, or in this case, it is 0. So you take 0, your lowest value, and you're going to evaluate 0 into this function. So we would have 1 plus 0 to the third, which equals 1. So our y1 equals 1, because our y1 was what we evaluated. Now the next x we're going to use, called x sub 1, in the past videos we used y. It doesn't really matter what you use. What you have to understand is that you started with 0, and now you add the increment of 1. So 0 plus 1 equals 1. So let's find y sub 1, which will equal f of 1. And let's substitute 1 into this equation. And we would get 1 plus 1 to the third, which equals 1 plus 1, which equals 2. So y2 equals 2. Now what's our next x going to be? Our x2 is going to be, what did we have before? You always take what you had before and add the increment of 1 plus 1, and we get 2. Notice that's our higher limit. So we started at 0, we had an increment of 1, and then we went up to 2, and that will be our last one. Now let's find y of 2, which would be the same as finding f of 2. So let's substitute a 2 into this equation. And we would get, into that function. 1 plus 2 cubed is equal to 1 plus 8 equals 9. So y sub 2 equals 9. And I see that I have an error there that this should be y1. Okay, so we have our three values. We have y1, oh my goodness, y1 equals 1, y2 equals 2, y1 equals 2. Oh my goodness. And this should actually be our y sub 0. I apologize for that. It should match the x's. So we have our three values. Now we use Simpsons rule. Simpsons rule says, here's what you do. You can approximate the area, which was 0 to 2, of 1 plus x to the third dx, approximates. And the formula is h over 3. And then in parentheses, it's y sub 0 plus 4, always 4, times y1 plus 2 times y2. And you alternate the 4 and the 2 all the way until you get to, lastly, your y sub n. So in this instance, we're going to have h over 3. Our h was 1, so we have 1/3 times y0 was 1 plus 4 times y1 was 2 plus 2. Whoops, we don't want to use 2 because this is our last value here. Since our last value is this one, we leave it alone by itself. So we don't want to multiply it by 2. We just want to list it as it is, plus 9. So note that the first value and the last value are left as is. The middle ones are multiplied alternately, starting with 4, then 2, then 4, then 2, and so on. And this approximates 1/3 of 18, which will approximate 6. Now, one really good way to check this, if you can, is to see if the function was easy enough to integrate directly. And this one happens to be. We have the interval of 0 to 2 of 1 plus x to the third dx. If we integrate this function, the first one would be 1x, and then this would be x to the fourth over 4. We're integrating each one of these. And we have to evaluate that from 0 to 2. So we start by saying 1 times 2 plus 2 to the fourth over 4 minus, and we would substitute 1 times 0 plus 0 to the fourth over 4, which is going to give us 2 plus 2 to the fourth over 4 minus 0, which in the end is going to give us 2 plus 4. Oh my goodness, what am I doing here? Let's write this a little bit neater. 2 plus 4, which equals 6. So notice in both cases we got 6. So that's just to show you that Simpsons rule does work. It approximates the area under the curve, or what we call the definite integral from 0 to 2. Okay, let's try another problem and see how we do. Problem number 4 is a nasty one, but we'll do it. We have the interval from 0 to 8 of x to the 1/3 dx, and you're told n equals 4. Okay, let's get our line a little smaller. So we first find h. So h is equal to, I don't like that one either. Let's go back and get a middle line. H will be equal to b minus a over n, which is 8 minus 0 over 4, which is 2. So we have increments or intervals of 2. Okay. we start with our lowest value, which is 0, and we know that our first x is going to be x of 0 is going to equal a, which equals 0. And we evaluate y0 at 0. So that would give us 0 to the 1/3, which just gives us 0. So y to the 0 equals 0. It's nice to put them over here on the side so when I go to do my formula, I have them all right at hand. Now, what would my x1 be? My next x that I'm going to evaluate is going to be what I had before, 0, plus my increment of 2, which equals 2. So now I find y sub 1, which is substitute the 2 into the equation, which would give me 2 to the 1/3 power. And using your calculator, you will get 1.25992,105. So y sub 1 equals 1.25992,105. That's our second value. Now what will be our next x? It will be what we had before, 2, plus the increment of h, which is 2, and that's 4. So now we find y of 2, which means we put 4 into this equation, and we would have 4 to the 1/3, which equals 1.587401,052. And I'll write that again as y2 equals 1.587,401. Okay, let's fix that 4. 401,052. That is our y2. Are we done yet? No, because we've only gotten up to 4 here, and our value has to go to b, which is 8. So x sub 3 is going to equal what we had before, our 4, plus our h increment of 2, which equals 6. We're getting closer. So y sub 3 is going to equal 6 to the 1/3, which comes out to 1.817120593. Y sub 3 equals 1.8171. Let's fix that. 817120593. Now, I'm not going to lie, in future problems I rounded to the nearest thousands because it just seemed easier. Your book, however, does not expect you to do that. They expect you to carry it out. You get very close, so I'm fine with you going 3 places or to the nearest thousands. Okay, we're not done yet. X to the 4th, we were at 6, so we do 6 plus, what's the next increment? 2. 6 plus 2 gives me 8. Yay, I've reached my upper limit. I know this is the last one. So y4 is going to be 8 to the 1/3, which, by the way, is the cube root of 8, which we know is 2. So y sub 4 equals 2. Now remember, let's remember that this value and this value are left alone. Do not multiply them by anything. This one will be multiplied by 4, this one will be multiplied by 2, and this one will be multiplied by 4. So let's write that out. We get the integral of 0 to 8 of x to the 1/3 dx is approximately, and I will have to finish this later, but your answer is 11.6553125.